My name is Tristan Lunscott, and this is my Lab 2 for Physics 2211, Motion of a Falling Object. The purpose of this lab is to understand and analyze the motion of a falling object and the forces acting on the object. We will do this by looking at and understanding gravitational and drag force. We will then create 3 models, 1 being experimental and 2 being computational. One of the computational models will include only the effect of gravity, while the other will account for both gravity and drag. We will then compare all of these models to help explain terminal velocity and the impact of drag forces on motion. Throughout this experiment, you will see how we determine that drag force is necessary when observing and comparing real-life experiments. Before the experiment, I will go over some important and relevant concepts. Some relevant formulas are the velocity and position update formulas, which are used in our computational models to predict the ball's position and velocity as a function of time. The force due to gravity is equal to the mass times g, which is the acceleration due to gravity here on Earth as 9.81 meters per second squared. This g is calculated by multiplying the gravitational constant times mass over the radius squared, not including the second mass because, in this case, the mass of the Earth is the only relevant mass. The drag force is equal to the proportionality constant multiplied by the instantaneous velocity squared. Next, an important principle is Newton's second law. For this experiment, we need to understand how Newton's second law, which states that the net force of an object is equal to the acceleration multiplied by the mass of an object, is important, and not simply F net equals Fg, and how our F net, which includes gravity and drag, is not zero. F net and Fg do not cancel each other out. Understanding this will help us see that the velocity of an object can change throughout motion. Here's a diagram showing the forces acting on the ball. The first diagram shows the unbalanced net force when drag force is less than gravitational force. In this diagram, the ball is not yet at terminal velocity, which is seen in the second diagram. This is when the drag force and force due to gravity are equal and opposite. Here in the second diagram, the net force is zero, and it will no longer accelerate and will maintain its terminal velocity. The key assumptions in this lab are motion is only in the y-axis, drag force is always proportional to the square velocity, and the force of gravity is constant. Here's my tracker video and me tracking my lacrosse ball's position versus time. I chose my axis so that down was negative, giving me my downward sloping position versus time graph. I used a timestamp of 0.067 seconds and established that the door handle from which I was dropping was a meter off the ground. For the first computational model, the one without drag and only gravitational force, I used the starter code and inputted the equations mentioned earlier. As seen in my code, the box's initial position is at 1 meter, and I inputted the mass of the lacrosse ball I was using, 0.14 kilograms. Initially, the ball is at rest, therefore the velocity is the vector 0, 0, 0. I started tracking at 0.395 seconds and inputted delta t as the timestamp of 0.067 seconds, as used in my video. Last, b is equal to 0 because the drag force is not being applied here. Next, in the other side of this code, we set the net force as the force due to gravity, which is the mass of the ball times g. For the second computational model, which includes both gravity and drag, there's a few differences. The main difference being the value of b, the proportionality constant, which is now 0.0525. I calculated this through trial and error until I found a value that gave me a final position equal to my tracker model's final position. Next, the net force is no longer just the force due to gravity, but now includes the drag force, which is calculated as Fd. Here are the GlowScript results for our 2 computational models, drag included on the right. Here's the graph that compares all 3 models. The computational model without drag, in orange, is the most different from our tracker data. It immediately curves downward more dramatically, over-predicting the ball's position in the negative direction the entire time. This is likely due to the missing drag force, which means that there is no force opposing the downward gravity force. The gray line, which represents the computational model with drag, is more similar to our tracker model and with a much more similar final position. This model overpredicted the ball's position in the negative direction as well, but just in the middle. This is likely due to human error and the drag force being larger than expected at the start and changing as it falls. To reduce this error, I could calculate the drag constant using more than just position and ensure that no other forces are on the ball for me. Additional questions. First, we were asked to examine the velocities of the computational models and find which predicted a terminal velocity. The terminal velocity is reached when drag force is equal and opposite to the weight. The only model that has drag force predicts a terminal velocity. The change in slope, starting to flatten out and become linear, represented on the graph, shows this. Next, we were asked to imagine the ball was initially thrown downward and if this would affect our terminal velocity. Their answer is no, it would not affect our terminal velocity and it would instead remain constant. This is because an object's terminal velocity depends only on the velocity needed to reach a drag force equal and opposite to its weight. Therefore, the starting velocity is irrelevant, and the object's terminal velocity is specific to the object, not the starting velocities. Thank you, and have a great day.